All right, team, let's jump right into today's explainer. As database architects, our ultimate goal is to move way beyond the basic concepts and really start executing advanced modeling. We want to build truly scalable, rock-solid databases right from the ground up. So today, I'm going to share the foundational best practices that we absolutely need to adopt as our gold standard. Okay, let's dive into this. I want to kick things off with a bit of a provocative question for you all. Why do most database systems actually fail? When systems completely crash under heavy load, or when data suddenly becomes corrupted, it is rarely just because someone wrote bad code. Almost always, it comes down to a poor foundational architectural design and data anomalies that were just completely ignored. And well, that's exactly what we're here to fix. So here's the blueprint for today's explainer. We'll be covering the database landscape, the 6 steps of database design, core modeling building blocks, navigating complex data relationships, and finally, choosing the right tools. These are the essential standards we'll use when building any system from scratch. Okay, Section 1, the database landscape. Let's take a quick look at where we came from. Our industry has moved incredibly fast, right? Back in the 1960s, data was structured in these highly rigid, tree-like hierarchical models. By 1971, the network model came along and gave us a bit more flexibility. But the real game changer? That happened in the 70s and 80s with the relational model. That's the tabular, highly organized structure we still primarily use. And today, we're building on top of that with cloud infrastructure and big data systems that handle just a massive volume, velocity, and variety of information. When you visually compare these historical models side by side, it's kind of wild. You can literally see how rigid that hierarchical tree is compared to the flexible, interconnected tables of the relational model. This structural logic is exactly why our team relies so heavily on relational databases. It lets us seamlessly link entirely disparate data points using keys, rather than relying on clunky, hard-coded parent-child paths. Moving on to Section 2, the 6 steps of database design. So walk through this strict 6-step blueprint with me. Steps 1 through 3, requirements analysis, conceptual design, and logical design, are where we gather intel from our users and draft high-level descriptions of the data. Now the real magic happens in the second half. Steps 4, 5, and 6 are where we refine our schemas, simulate actual workloads to hunt down physical weaknesses, and finally, lock down our security design by defining user roles. We aren't just slapping tables together here, we are engineering architectures. And arguably the most absolutely crucial part of this is what happens during Step 4, schema refinement. This is where we perform normalization. Think of normalization as your ultimate safeguard. It's a strictly mathematical process that strips out data redundancy. If we skip normalization, an update in one place might not sync somewhere else, leaving our entire system in a dangerously inconsistent state. We definitely don't want that. All right, Section 3, core modeling building blocks. Let's talk about the actual materials we use to construct our blueprint. Before we even think about writing a single line of SQL, we map our logic using the entity relationship, or ER model. The ER model rests on a simple triad. Entities are your distinguishable real-world objects, say a customer or a loan in a banking app. Attributes are the properties describing them, like a customer's physical address. And relationships? Those are the associations. If a customer borrows a loan, that borrower action is the relationship itself. Now, how does this translate into real-world constraints? Through mapping cardinalities. We use these to dictate the exact number of entities that can be associated with another. So, if a customer can only ever have one account, that's a strict one-to-one relationship. If they can hold multiple loans, that's one-to-many. Defining these rules up front is how we prevent catastrophic logical errors later on. Now, to our junior developers tuning in today, please pay very close attention to this next part. You have to use extreme care when selecting your primary key. A superkey is just any set of attributes that identifies an entity, and a candidate key is a stripped-down, minimal version of that. But the primary key, that is the one you manually select to anchor the entire table. Make absolutely sure the attributes you pick guarantee uniqueness and basically never, ever change. Section 4, navigating complex data relationships. Let's be real. Real-world scenarios are messy. You won't just be plugging customers into accounts. You're going to deal with complex, overlapping dependencies. Look at the contrast between strong and weak entity sets.
A strong entity has its own primary key. It can stand alone. A weak entity does not. Its very existence depends on an owner entity. Think of a payment. A payment record floating in the void means nothing on its own. It inherently requires a lone entity to actually make sense in the system. Spot your weak entities early.
We also have to figure out how to model subgroups properly. We can use specialization, which is a top-down approach, taking a really broad entity like person and explicitly breaking it down into student or instructor. Or we go the other way with generalization, a bottom-up approach that synthesizes commonalities. Whichever you choose, both methods result in vital attribute inheritance, meaning the subclass just automatically inherits the properties of the superclass. Okay, here's a curveball you will for sure encounter. What do you do when a relationship itself has its own data? Let's say an employee completes a certification course. The date completed doesn't belong to the employee table, and it doesn't really belong to the course table. It belongs to the specific event of completion. When a relationship holds unique attributes like that, we have to convert it into an associative entity.
And for our senior engineers, here's a really neat architectural trick: aggregation. The standard model actually restricts us from expressing relationships between relationships. But what if you need to track which manager is overseeing an employee's specific project assignment? By using aggregation, we basically draw a big box around that employee-project relationship, treat the whole thing as a single higher-level entity, and then link that directly to the manager. It perfectly resolves ternary limitations, and zero redundant data is created.
Section 5. Choosing the right tools. So we've covered the methodology and the building blocks. Now, what do we actually use to draw these architectures? As your lead architect, here are my direct recommendations. For steps 1 and 2, just use Draw.io. It's incredibly fantastic for those high-level conceptual diagrams. Once you hit step 3, shift over to MySQL Workbench. It is robust for practical implementation and automatically generates diagrams from your existing schemas. And hey, if you just need fast modern design using simple text scripts, dbdiagram.io is an incredibly efficient choice. I want to highlight this golden rule pulled straight from our engineering documentation. Only a careful design will eliminate problems. You might draw 3 different schemas on a whiteboard, and they might all look totally plausible. Database architecture is absolutely as much an art as it is a strict science. It takes patience, iteration, and a really deep understanding of the underlying business logic. So I'll conclude our explainer today by challenging you all. Take a look at the tickets in your current sprint. How are you going to take these 6 steps, these strict rules on normalization and key selection, and apply them to architect your next big project? If you design it right the first time, you won't be waking up to a server fire at 3 a.m. to fix it later. Thanks for your focus today, team. Now let's get back to building great systems.